New unit starting today on magnetism. Let's define a couple of terms about magnetism before we really get into the meat and potatoes of it. First one is what we call a magnetic domain. The definition of this, when you read it, isn't probably going to make a whole lot of sense to you. We'll talk about it, we'll discuss it, we'll elaborate on it, and hopefully it'll make some sense to you when we're finished. A magnetic domain is a tiny little region inside a ferromagnetic material that's represented by an arrow. So what does that mean? Well, we have to know what a ferromagnetic material means first. A ferromagnetic material is a material that can become magnetized. What's a chemical symbol for iron? Anybody know? Fe. Where do you think that comes from, Fe? Yeah, Latin. And it's... What do you think the most common example of a ferromagnetic material is? Give me an example of a ferromagnetic material. This is an easy question after what I've just said. Iron. It comes from the Latin word for iron. Ferromagnetic material is a material that can become magnetized. Iron is probably the most common example of a material that can become magnetized. Now, there are other examples. Another very common example is steel. But of course, steel is just an alloy of iron. So it's magnetic because it contains iron. Tiny little region inside a piece of iron or steel or some other ferromagnetic material that's represented by arrows. Here's my piece of iron or steel or whatever ferromagnetic material we have. Here's my little regions inside this ferromagnetic material. Here's my little arrows representing these little magnetic domains. They're pointing in random directions. Now understand, if you look at this ferromagnetic material under a microscope, you're not going to physically see arrows. We're using arrows to represent domains. What really happens inside here is a lot more complicated than just a bunch of arrows. Electrons are spinning in crazy directions. When we get similar patterns of electron spins, we get a domain. We represent that domain not by trying to draw a whole bunch of electrons spinning around, but we represent it by just simply drawing an arrow. So each of these domains with each of these arrows represents a different domain with different patterns of electron spin. This ferromagnetic material is not a magnet right now. It has the ability to become a magnet. It can become a magnet, but it's not a magnet yet because these domains are randomly aligned. They're pointing in random directions. If I want this to be a magnet, then I've got to cause these domains to point more or less, at least, in the same direction. And there's a couple ways that I can do that. One way that I can cause these domains to align in the same direction, and therefore form a magnet here, is to bring another magnet nearby. Here's a magnet with a north pole and a south pole. That magnet has domains in it as well that are already aligned. Those already aligned domains will have an effect on these domains in the non-magnetized ferromagnetic material. They will cause these domains to become more or less aligned, more or less pointing in the same direction. They're going to point like this. Exactly parallel, exactly aligned? No. The more aligned they are, the stronger the magnetic effect of this new magnet is going to be. But we're still going to have some magnetic effect in this new magnet here because the domains are now somewhat aligned at least. What's the polarity of it become? Well, it's going to match up with the magnet that was brought nearby it. North pole and a south pole. Notice which way the domains point. Domains are always going to point away from the south and toward the north. Now the other way that I can do this, that I can align these domains, is to take a wire and wrap it around. You guys have probably all made electromagnets at some point in grade 5 or grade 6 or whatever science class you do some of this stuff in. You wrap wire around a nail or something. Right? You apply an electric current attached to batteries, and you try to pick up thumbtacks or whatever. Have you ever done that? You had to have done that in junior high school or elementary school at some point. That's what's happening here. We wrap this wire around it. We apply an electric current. That causes a magnetic field. That magnetic field causes the domains in this non-magnetized ferromagnetic material to start aligning themselves. It becomes a magnet. What happens when I remove the current? Well, it goes back to the way it was before. The domains all point in random directions again. But as the electric current is flowing, these domains become aligned. So there's two ways to do this. Two ways to cause these domains that are represented by arrows to point in the same direction, making it a magnet. One, bring another magnet nearby. Two, wrap some wire around it and apply an electric current. Make it into an electromagnet, basically. Let's talk about a couple of laws of magnetism. 3, actually. 3 laws of magnetism. Who remembers the 3 laws of electricity? Who remembers the first law, even, of electricity? Michael? That's the law of conservation of charge. That's correct, but it's not one of those 3 laws that we talked about. Opposite charges attract, like charges repel each other. Okay, we're not talking about charges now. We're talking about magnetism. Instead of charges, we've got poles. Instead of being a positive charge, we've got a north pole. Instead of being a negative charge, we've got a south pole. We're going to say that like poles, just like charges, are going to repel each other. They're going to push each other apart. Similarly, we're going to say that unlike poles, just like unlike charges, attract each other. So north repels north, just like positive repels positive. North attracts south, just like positive attracts negative. What was the third law of electricity? Third law of electric charge. Remember that one? Charged objects attract neutral objects. Yeah, again, we're not talking about charges now. We're talking about poles. What would be analogous to a charged object? An object with poles? Well, what's a simpler name to describe an object with poles? A magnet. So a magnet will attract something that's non-magnetized? Well, not quite. A magnet will attract non-magnetized objects, but only some of them. If you bring a magnet nearby the leg of your desk, it'll attract. If you bring a magnet nearby the piece of paper sitting on top of your desk, it won't attract. So magnets will attract some things that are not magnetized, but not others. What's the difference between the leg of your desk and this piece of paper that I'm holding up right now? Metal? Material? What's the word I'm looking for? Ferromagnetic. Okay, the paper isn't ferromagnetic, the leg of the desk is. So magnets will attract not all non-magnetized materials, but all non-magnetized ferromagnetic materials. Both north and south poles of a magnet will attract non-magnetized ferromagnetic materials. Ultimately, you need a ferromagnetic material because you need domains to be aligned. You can't have domains aligning themselves if you have a material that doesn't have domains. So what we do, we bring a magnet nearby. It's attracted because it temporarily aligns the domains in the leg of your desk. It temporarily causes those domains to point in the same direction, which makes it a temporary magnet. That temporary magnet will be attracted to the magnet that you brought nearby. It's kind of like charged objects attracting neutral objects. Why did that happen? Because of a temporary separation of charge. We caused induction to take place, right? We temporarily separated the charges. Here, we're not separating charges or separating poles, but we temporarily cause an alignment of domains. When I bring the magnet away, take it away, then the domains go back to where they were before, just like the electrons in the neutral object went back to where they were before. Told you I had more where that one came from. So the nail is saying to the magnet, I find you very attractive. How come? Why is the nail saying to the magnet, I find you very attractive? Because the nail is a non-magnetized ferromagnetic material. The magnet is a magnet. And magnets attract non-magnetized ferromagnetic materials. Wait a second. We said magnets attract non-magnetized ferromagnetic material. Does it go the other way around? Newton's third law says if a magnet attracts a nail, then a nail is going to attract a magnet as well. Okay, so what happens in this nail here? This magnet's got its poles, north and south pole, right? What happens in this nail? The domains that are inside this steel nail are going to become temporarily aligned, so they're going to point all in the same direction, more or less, for a brief time, and it's going to be attracted toward this magnet. All right, let's talk about magnetic fields. We talked about gravitational fields, we talked about electric fields, now we're going to talk about magnetic fields. To introduce this, start this off, I'm going to give you a piece of paper here, a little handout with some pictures on it. Then we're going to do a little activity with these pictures and some magnets and some compasses. On this handout, you're going to see 3 diagrams. This one's the first one, this is the second one, and this is the third one. The first one, you can see it has one simple magnet with a north pole and a south pole. It has a bunch of stars around it as well. The second one is going to have 2 magnets, but this time we've got a north against a south. The third one also has 2 magnets, but this time a north against a north. There's a bunch of stars surrounding all 3 of these diagrams. These stars represent places where I want you to put a compass. So I want you to put a magnet or 2 magnets, whatever the case may be, in the middle of your desk, away from the edges. Why do you think I want you to keep the magnets away from the edges of your desk? So they don't get attracted to the legs of the desk. Good. The frame of the desk is steel. It goes around the edges of the desk. If you put the magnets nearby that, then it's going to be affected by the steel in the desk, right? Just like the nail was affected by the magnet that we saw in the last diagram there. Put it in the middle. Orient it like you see in the diagrams on your page. Then I want you to put your compass in various places as indicated by the little stars. Every time you do that, I want you to see which way your compass is pointing. I want you to draw a little arrow at each of those stars indicating which way the compass is pointing. So if I get a compass pointing downward when I place it in that position, then I want you to draw a little arrow downward. Okay, if there's a compass pointing down and to the left in this position, then I want you to draw a little arrow down and to the left. Make sure it's short, okay, and make sure it's drawn as accurately as possible. What we're going to do is hopefully start seeing some patterns of these arrows after we've drawn these diagrams. And we'll be able to draw the magnetic field diagrams by observing actual magnetic fields with these compasses. Okay, does that make sense? All right, if I can get one person from each group of 2, let's say, I guess we'll have to have one group of 3 here, to come on up and get a compass and to get a couple of bar magnets out of this box. That'd be great, please. All right, what do we get when we drew these out after observing which way the compass pointed and placed in the field here? We should have got arrows that looked more or less like what I'm going to draw on the board here. Okay, you get an arrow here. You might not have gotten exactly this, but again, it should be relatively close. How many people got something that looked kind of like that, more or less like that? Right? If we start connecting dots there, we're going to get something that looks like this. That's going to look an awful lot like the electric field surrounding a positive and a negative charge. So the electric field surrounding a positive and negative charge is not the same thing as a magnetic field. Magnetic field, by the way, given by the symbol B. It's not the same thing, but the shape of it will be identical. Positive is like North Pole. Negative is like South Pole. Let's draw the next one. Start drawing some arrows here. Should look something like this. Okay, so the arrows start looking something like that. When we start connecting the dots there, connecting the arrows, it's going to look like this. And again, we get a pattern that looks a lot like we did when we drew some magnetic fields or electric fields, in the last unit. Let's say we got a positive here, a negative here, a positive here, and a negative here. The field lines between the positive and negative in the middle are going to look something like this. And then, of course, we've got this. So again, you introduce a positive and negative charge, another positive and negative charge, you get an electric field. When you introduce two magnets north against south, we get a magnetic field that looks exactly the same as the electric field. Two different things, right? Electric field, magnetic field, two different things that look exactly the same, and it's not a coincidence that they do look exactly the same. Last diagram. Last diagram should look something like this. I'm just going to connect the dots kind of on the fly here as opposed to drawing the arrows. Should look something like this. What does that remind us of? Well, if we had two positive charges right here and here, and then a couple negatives over here and over here, then we should get an electric field that looks the same as the magnetic field that we just drew. The electric field different than the magnetic field, but the electric field exactly the same shape as the magnetic field. Now, all of these fields are what we call non-uniform fields. We know what that means, right? A uniform field is a field that's constant. It's the same value everywhere. These are all non-uniform fields. How do we know these are non-uniform magnetic fields? What in the diagrams tell us that these are non-uniform fields? The field lines are not, starts with a P, parallel. They're not parallel. If the field lines are parallel, it's a uniform field. The field lines aren't parallel. It's a non-uniform field. Okay, it tells us that the field has a different value depending upon where it is. Now, there are certain averages that we can find, or certain averages that we can assume. For instance, although it's a non-uniform field, the average magnetic field surrounding the Earth is about 10 to the minus 5 Tesla. The unit, by the way, the symbol is B. The unit is the Tesla. It varies. Okay, it's not 5 times 10 to the minus 5 Tesla everywhere, but on average, it's about 5 times 10 to the minus 5. By the way, you don't need to memorize all these numbers. You don't even need to write them down if you don't want to. I'm going to give you a bunch of different magnetic field strengths only for perspective, so that you know the magnetic field caused by the Earth is actually pretty weak. We think it's strong, but it's not. It's really pretty weak. It's about, in fact, 1,000 times weaker than the magnetic field surrounding a typical bar magnet. Now remember, these are non-uniform fields, so these are average values. But even if we take average values, we can get an idea as to relative magnitudes. Okay, one is 1,000 times stronger than the other. Why do you think when you move the compass nearby the magnets, in the activity you just did, that the compass was no longer affected by the Earth? I stand over here and I hold the compass in my hand, it's going to point that way towards Calgary. But if I bring it nearby a magnet, it points toward the magnet. Why does it no longer care which way is Calgary, which way is north, which way is south? Because it's more affected by the bar magnet. As weak as the bar magnets were that you used, it's more affected by those than it is by the Earth. Because the strength of a bar magnet, even a weak bar magnet, is much stronger than the strength of the Earth's magnetic field. What's a sunspot? Somebody in the last class said it's like a little explosion on the sun. Well, it's like a big explosion, actually, on the sun. The sun is big, and it creates these big explosions on the surface of the sun. And when it does that, it releases these charged particles. This sunspot is magnetic. There's a magnetic effect there. The strength of the magnetic effect there is 10 to the minus 1 Tesla, so about 10,000 times stronger than the Earth's magnetic field. Now, it ejects these charged particles. These charged particles go everywhere through the solar system. Some of them come towards the Earth. When they come towards the Earth, they'll get deflected by the Earth's magnetic field, and we'll describe how that happens in a few days. As they get deflected by the Earth's magnetic field, we see something. We observe them. We observe them as... Anybody ever been up here by the school at 11 o'clock at night? The odd time you'll see this up here. Nope. Northern Lights. You don't see it all that often as far south as we are in Okotoks. You see it a lot more often in Edmonton and north of Edmonton. But you can see them sometimes from out here by the school because it's so dark here, right? So dark out here. I'm sorry? Is that right? Where do you live? Okay, yeah, that makes sense. So these charged particles come and they get deflected by the Earth's magnetic field. The Earth's magnetic field, which is very, very weak, but still strong enough to deflect these charged particles and cause the northern lights. How many people have ever had an MRI? 1, 2, quarter of the class here. An MRI. I had one on my knee once. The thing that bothered me the most about the MRI on my knee, to be honest, was being forced to lie there in this machine that's about the hole that you go into. You literally go inside this machine, and the hole that you go into is about this big around. It's barely big enough for you to get in. And they tell you, this is going to take about 25 minutes. Don't move. That's very difficult. I mean, I can sit somewhere in one place for 25 minutes, but when somebody tells me, don't move, don't even twitch, it's like, well, that's when you start twitching. And that's when your knee starts like twitching around. Right? I found it very, very difficult. I hated it. And I was lucky enough that it was on my knee, so only half my body was inside this machine. You have it on your upper body, and your whole body is inside this claustrophobic machine. When you get an MRI, they give you this big questionnaire ahead of time. If you guys have had MRIs, you probably remember some of the questions, like, do you have any piercings? Have you ever had metal in your eye? You know, like metal chunks, shards of metal in your eye, and you know, all kinds of things. Like it's a couple pages long, this thing. Why do they care about that stuff? Why do they care if your belly button is pierced? Why do they care if you had a little steel chunk in your eye at some point, if it's not affecting your eyes? Why do they care about that? It could mess up results. Sure, it could mess up results. What else? Yeah, if it's a ferromagnetic material, if it's steel, which most metal chunks that you would have embedded in you for whatever reason would be probably steel, or at least some kind of steel component, then it would be affected by a 15 Tesla magnetic field. 15 Tesla. That's 1.5 times 10 to the 1. That's 1 million times stronger than the Earth's magnetic field. I don't know what kind of negative effect that would have if you had metal chunks in your eye, but I can't imagine it would be good if you've got a 15 Tesla magnet trying to suck them out. Okay, I wouldn't think it would be very good. I don't know what they do if you actually answer yes to any of those questions. My dad worked in construction his entire working life, and he's got metal chunks all over his body, including he's got a piece of steel to this day embedded in his arm. You can actually feel it. If you put your finger over his arm, you can feel this chunk of steel that got embedded in his arm one day while he was working. He had an MRI on his back. I'm not sure what they did, or what the big deal was. In the end, it didn't get sucked out of his arm and whatever. But they ask you that question because obviously it can be a big deal with that strong of a magnetic field. Finally, look, if you've got metal in your eye and you want to stay away from an MRI machine, then you probably want to stay away from the strongest human magnet ever made, which is about 2.5 times the strength of an MRI machine. Same order of magnitude, but about 2.5 times the strength. Or, listen, if you're going to stay away from both of these, you sure as heck better stay away from a magnetic neutron star. Even if you weren't incinerated long before you ever reached it, you probably wouldn't want to get near it, because the strength of the magnetic field produced is, on average, about 10 to the 11 Tesla. That's 10 to the 16 times stronger than the Earth's magnetic field. I would suspect that's probably a strong enough magnetic field to literally suck the iron right out of your blood. By the way, iron in your blood, is it the same kind of iron that they mine out of the ground? Absolutely it is. It's exactly the same thing. If you take, it's just in tiny little chunks. If you take, you buy cereal, sometimes it says fortified with iron. You ever see that? If you take cereal that's fortified with iron and then you grind it up, you can actually suck the little chunks of iron out of it with a magnet and see them. You can see these tiny little black chunks of iron that you've sucked out of your cereal. That's exactly what you're consuming, because that's exactly what you need in your body. It carries the oxygen to your brain. So don't get close to one of these, because it's going to suck the iron out of your blood, and then you're not going to be able to function because the oxygen won't go to your brain. And that's if you weren't killed long before you ever got there. Don't memorize these numbers, but just kind of remember the Earth's magnetic field is really, really weak. A bar magnet is quite a bit stronger than the Earth's magnetic field. An MRI way stronger than that. Okay, little things like that. Not exact numbers, but just where they kind of fall. This is just a little comparison of the three fields that we've talked about thus far in Physics 30, the gravitational field, the electric field, and the magnetic field. The source of gravity, of course, is mass. The source of an electric field, of course, is a charge. And the source of the magnetic field? A ferromagnetic material with aligned domains. What's a one-word synonym for that circle? What's a one-word synonym for ferromagnetic material with aligned domains? I'll give you a hint. It's an easy one. No? No? Steel, iron, both good guesses. Sorry? A magnet. And we could replace that entire thing with the word magnet. Now, the direction of a gravitational field is always attractive. We don't know about any kind of repulsive gravity force, right? Masses always attract mass. It's toward the producer, toward whatever causes it. Whereas an electric field can be attractive or repulsive depending upon what kind of charges you have. The field is the way that a positive moves when placed in the field. It's away from the positive, it's toward the negative. And finally, the magnetic field is also attractive or repulsive depending upon which poles you have. North pole, south pole, north pole, and so on. It's the direction that a compass points when placed in the field, from north to south, away from the north toward the south. Last thing, we see a picture of the Earth here, and the magnetic field that surrounds the Earth. We know it's a weak magnetic field. It's about 5 times 10 to the minus 5 Tesla, although it does vary, because these field lines are not parallel to each other. It's not a uniform field, but about 10 to the minus 5 Tesla. We can see that these field lines are pointing upwards towards Canada. What seems wrong with this picture, though? Michael? South is on the top, north is on the bottom. Is there something wrong with this picture? Well, let's look at the definition of the direction of magnetic field that we learned a few minutes ago. We defined the definition of direction of magnetic field as the way that a compass needle points when placed in the field. So let's draw the equator here. Here's the equator, somewhere around the center of the Earth there. If I'm standing at the equator with a compass, which way is it going to point? Towards Antarctica or towards Canada? It's going to point towards Canada. So therefore, the diagram is drawn correctly. The only issue now is whether it's labeled correctly. What's the other definition of the direction of a magnetic field? That a compass points when placed in the field and from north to south. Do these field lines point from north to south the way I have it labeled? Yes. So this is drawn correctly. Geographically, this is the North Pole, and this is the South Pole. But magnetically, that's not the case at all. Magnetically, this is the South Pole, Canada is the South. and Antarctica is the north, magnetically. Now, we never think of it that way. We don't even navigate that way, even when we use compasses. We think of Canada as being north and Antarctica as being south. That's okay. As long as everybody's on the same page and we all call it the same thing when we're navigating, it's okay. But understand that it's wrong. Understand that Canada is not North Pole and Antarctica is not South Pole magnetically. It's the other way around. Geographically, it's the way that we've always thought of it. Canada is still north, Antarctica is still south, but magnetically, that's not the case. That time when you were 7 years old and you didn't get what you asked Santa Claus for Christmas, we now know why. Because you thought Santa Claus lived in the South Pole, sorry, in the North Pole. Really, now you know that Santa Claus lives in the South Pole. The penguins, you thought lived in the South Pole, now you know they live in the North Pole. So when you sent that letter to Santa, it probably just got misdirected. Probably went to the wrong place. You addressed it North Pole. Somebody at the post office said, oh, okay, it's gonna, whatever. Somebody just got mixed up with the whole deal. Santa Claus lives in magnetic South Pole, and the penguins live in magnetic North Pole. Got it? You got a letter back? You should compare it with anybody else's letter back and see what it says. Okay, that's it for the day here, guys.